Okay, I wanted to work for you another circuit problem, and it occurred to me I hadn't used a ideal current source in any of the examples, so I wanted to go ahead and do that. So in this problem, you have a two-loop circuit, and there's an independent current source of 150 milliamps. And what we want to do is find the power associated with any given resistor. I just chose a couple of these to show you how you would get that going. The 2 ohm resistor down here and the 5 ohm resistor over on this side of the circuit. Okay, so I'm looking at this, and if this were like an exam problem, how I would think of it is, I'd look to see, well, if I want to know the power associated with the 2 ohm resistor, if I know either the voltage across it or the current through it from Ohm's law, I can get the other thing, so if I know the voltage across it, I can get the current through it using Ohm's law. And, I also know the formulas for power for resistance is I squared R or V squared over R, all right? So right away I'm thinking, I know the current through this 2 ohm resistor, right? Because it's a current source. So what I know is that this is 150 milliamps, okay? So the power for the 2 ohm resistor is going to be I squared, so 150 times 10 to the minus third amps. Okay, that's what the milli's for. You put the 10 to the minus 3 to take care of the milli. All right, I square that and multiply by 2. All right, and when I do that, I get 0.045 watts, which is 45 milliwatts. Okay, so easy enough. I wanted to point that out, that sometimes, the things we ask for on exams or at least part of it is really easy, right? Okay, so next, let's talk about a strategy to get the 5 ohm resistor power value. And, you can think your way through this, and what I'm hoping that you've gotten to the point of being able to do is look at equivalent resistance and coming up with equivalent circuits. Okay, so my eye is drawn to looking at this particular branch. If I had this branch current, I'd be good, right? And I know that all these are in series, and so this equivalent resistance for this branch is 61 ohms, right? You just add these together. 16 plus 5 is 21, plus 40 is 61. Okay, so that's good. And since I know the current coming here, right, if I combined this resistance with R equivalent on that branch, I would get this down to a simple circuit that looks like this. Okay, I still have the 2 resistors, and I would have let's call it R1. All right, so the 2 resistors would be 47 and 2, and this is 150 milliamps. All right, so R1 is the parallel combination of 61 in parallel with the 22. So that'd be 61 times 22 over 61 plus 22. So we have that value. All right, now I could get the voltage V1, because that's just going to be the current, 150 times 10 to the minus third. So there's the current, times R1. All right, so I did that calculation, and I get, let's see, I did that somewhere, hang on just a second. Yeah, I get V1 to be 2.4253. You see where I have all the numbers ready to go. R1 is this, and V1 is this, okay? So now I have that, I know this voltage plus minus 2.4253. Well, since I know this voltage plus minus, I can get the current flowing through this branch because the equivalent resistance is 61. So I do this current I1, I'll call it I1, is the 2.4253 divided by the equivalent resistance. Okay, so I now have I1. So if I want the power of the 5 ohm resistor, it's just going to be I1 squared times the resistance value, which in this case is 5. Okay, so let me calculate that for you. What I get is 0.0079 watts. Which is 7.9 milliwatts. Okay, so that gives you an idea of how you can do a circuit analysis on a circuit that has an ideal current source. All right, so the advantage of an ideal current source is you actually know the current that's produced by the source. All right. Okay, so hopefully this example helps.